It's time to learn how to use Fischer projections to represent stereoisomers. Okay, we ended our last video with life is chiral. And in fact, glucose exists in nature as a single enantiomer. That's pretty cool. And I'm just wondering, how many stereoisomers does this molecule have? At this point, you all should know how to attack that problem. There will be 2 to the n stereoisomers, and then you might have to account for a mesoisomer. But for this particular molecule, you won't. Like, think about it. There's not going to ever be a mirror plane of symmetry because these 2 groups on the end are not the same. So it's just going to be 2 to the n, where n is 4. There's 4 stereocenters. So that means that there are 16 rather, stereoisomers of glucose. Excellent. Who wants to draw them all? No one wants to draw them all. All right, let's take a look here and see if we can use our model to understand Fischer projections better. So what we want to do is want to get that carbon backbone in the plane of the page, so just like this, and then you want to imagine flattening the molecule out like a worm, basically. I don't know, to me it's like a worm. It's like a dead centipede, because now you're going to have the substituent sticking up out at you. So you can see, just like what we drew, the hydroxyl is on the right side of the Fischer projection, and the hydrogen is on the left side. Okay, we're going to take it up a notch. We're going to convert the zigzag representation. So zigzag just means that the carbon chain looks like this. It is a staggered conformation, and it's the normal lowest energy conformation of any alkyl chain. So that's all zigzag means. So we're going to convert the zigzag representation of D-glucose to a Fischer projection. And before we do that, we can just think about the basics of how this is going to look. So the convention is that the highest priority carbon, so that's the aldehyde carbon, carbon 1, it's going to go at the top of the Fischer projection. And then from there we have our 4 stereocenters, and then we'll have our CH2 OH. Okay, so we have carbon 1, 2, 3, 4, 5, carbon 6. All right, okay. Now, we know that this is D-glucose, so that tells us that that last stereocenter is going to have the OH on the right, because this is derived from the stereocenter of D-glyceraldehyde, which has its hydroxyl on the right. Okay, now I'm going to tell you a dirty secret about, this only applies to sugars. So when you have sugars, if the stereocenter is R, then the hydroxyl is going to be on the right side of the Fischer projection, as long as you have the highest priority carbon at the top and the CH2OH at the bottom. If the stereocenter is S, then the hydroxyl is going to be on the left, and I only want you to do this use this shortcut rather, for carbohydrates. Don't do it for anything else. May or may not work. So what you can do right now is you can stop and you can assign the configuration of all the stereocenters and then follow the shortcut. That's up to you. But then I'll also show you with the model. Okay, if you pause and assign the stereo or the configuration of each stereocenter, you'll have R, R, S, and R. So that means that on carbon 5, you will have the hydroxyl on the right. On carbon 3, you'll have the hydroxyl on the left. It was S. And on carbon 2, the hydroxyl on the right because it was R. Again, please only use this shortcut for carbohydrates, and maybe don't use it at all. But now we're going to take the model, and I'm going to show you how to use your model to convert the zigzag representation to the Fischer projection. All right, y'all, let's do this. So this is what it looks like to have the chain, carbon-carbon chain eclipsed, and all the substituents are pointed out at you. So we're going to try to flatten this chain out, and we're going to flatten it out like this, where we have the highest priority carbon at the top. And what you should see is you have your hydroxyl to the right on carbon 5, to the right on carbon 4, to the left on carbon 3, to the right on carbon 2. All right, so I have here for you, I have a little screenshot from that demonstration next to the Fischer projection, and you can see how we can use the model to draw the Fischer projection. We got exactly what we did when we tried it on paper. Okay, here are 8 of the glucoses. These are the 8 glucoses, these are the 8 of the stereoisomers of glucose. They're called hexoses because they have 6 carbons. These are the ones derived from D-glyceraldehyde, like D-glucoses. And of course, there would be the 8 enantiomers. So each of these has an enantiomer. If you drew that, you would have all 16 stereoisomers of glucose. So I hope that at this point we have achieved all of our learning objectives, specifically in this video, the ability to draw Fischer projections. You should go and practice this now. This is something that you're probably not going to get until you practice. Okay, thanks for watching.